introduce Sara Johnson, who's been doing research with me in my lab across the hall. But I want to mention a few things about Sara before we start. Sara comes from us from Illinois Math Science Academy, where they have a very interesting cheer for the bowling team that I'm sure that if you ask her very nicely, she'll do the cheer. She was on the bowling team. But Sara is the quintessential Mauritian from my point of view, because she's a very passionate person about a very large number of things. For instance, she's passionate about swing dancing. Just put on a Charleston and she'll go wild. Geometry. Sara's passionate about geometry. She's the only person I know who has a favorite platonic solid. The icosahedron. Which, if you're going to pick a favorite platonic solid, that's it. She's passionate about writing. She started the Creative Writing Club and has several novels in the work, I believe. Baking. She's passionate about vegan, gluten-free baking in particular. If you like the cupcakes that she has back there, place an order. She'll be starting a baking factory. She's passionate about Doctor Who. She'll print out plastic models of the TARDIS for you. She's also a chemistry Spanish double major. So if you don't get enough of Sara today, she's going to be in a short play next Saturday in the cinema. It's a Spanish play, but it's going to be presented first in Spanish, then in English for those of us who don't speak Spanish. Lastly, she's passionate about her research. And I'm sure that you will get a sense of that from the talk you're about to hear. So without further ado, let me turn over the stage to Sara Johnson.
Thank you so much, Professor Stork, and thank everybody else for coming to hear me talk. So, like Professor Stork said, I'm going to be giving a talk on the research that I've been working on for the past 3 years. The title of the talk is Photodynamic Cancer Therapy, Self-Cyanide Porphyrin Adduct Synthesis and Single Oxygen Generation. If you don't understand some of those words, or all of those words, don't worry, I will explain them to you. So let's start out really, really basic. What is cancer? Normally, our cells grow and they divide and they do what they're supposed to do. But every so often, there's rogue cells. They grow too fast, they want to divide all over the place, and they don't want to play nice with the other cells. So usually our bodies are pretty good at getting rid of these rogue cells, but occasionally that doesn't happen. In that case, you can get a growth. You can see these naughty blue cells here. They're just going wild. So when our bodies can't get rid of these rogue cells, it can turn into tumors, and occasionally it can turn into cancer, which, as we all know, not so good. So there's a couple things you can do to treat cancer. The first is surgery. You can just cut out the offending cells. Now, this is a pretty good option, but it only really works if the cancer hasn't spread to other parts of the body. And there's quite a few side effects. You have to go through, surgery, which is really, really invasive, and then there's recovery time. It can also be really, really expensive. So there are a couple of other options. One being radiation, where X-rays, gamma rays, or other rays are targeted towards the tumor in your body, and basically it destroys the DNA of the cells. And then they're so damaged that they can no longer live, and the cells kill themselves, basically. Chemotherapy also acts by damaging those tumor cells. Now, chemotherapy is a family of drugs that you take, and they accumulate in rapidly dividing cells. So they accumulate not only in the tumor cells, but also in your hair follicles and in cells in your digestive tract, and also like red and white blood cells that divide a lot. So you can get a lot of really nasty side effects, as we all know, from chemotherapy. And then the one that I'm really particularly interested in is photodynamic therapy, which also acts by damaging the cells, the tumor cells, the cancer cells, but it works with light, which I will explain. And really the point of photodynamic therapy, which is not true for the other two that I mentioned, is that it works by generating singlet oxygen within the body, which is really reactive and then acts to destroy DNA and proteins. So singlet oxygen is an excited state of ground state molecular oxygen, so the oxygen that's just floating around in the air that we breathe. It has more energy than regular oxygen, and also the quantum state. Now to explain both of those, this is a molecular orbital diagram for molecular oxygen. In case you don't remember Gen Chem or didn't take Gen Chem, these horizontal lines represent orbitals, and then the arrows, the up and down arrows, represent electrons. Each orbital can hold 2 electrons, and on the bottom you have low energy going up to high energy on the top. So electrons fill those orbitals starting at the lower energy, then going up, and then when you get up here to the pi star 2p orbital, you'll notice that there are 2 orbitals at the same energy level. Now electrons don't really like to be together if they don't have to be, so the 2 electrons you'll notice will split into those 2 separate orbitals because they just want to be alone. So this is what ground state molecular oxygen looks like. Now singlet oxygen, the oxygen absorbs energy, and in case you didn't notice, those electrons have now paired. So ground state, excited state. So what is meant by the quantum state is that that's just these 2 electrons being paired instead of having 2 unpaired electrons in the 2 orbitals. And a lot of organic molecules have quantum states that look like this. They don't have that 2 electrons in the same orbital. So this molecule, this energy state, is they're more reactive with most organic molecules in our body. So singlet oxygen is used in photodynamic cancer therapy because it reacts in the cell. Like I said, we breathe in oxygen. It's everywhere because our cells use it for respiration. It's available in our cells. So photodynamic cancer therapy takes advantage of that oxygen that's already available, excites it to singlet oxygen, and then singlet oxygen goes and destroys DNA and sometimes proteins to the point that the cells are so damaged that they can no longer survive. Okay, so the main parts of photodynamic cancer therapy, there's 3. The photosensitizer. This is a porphyrin, and this is boron subphthalocyanide chloride, which I will call sub-PC for the whole presentation. They're both known photosensitizers, which means they're able to transfer energy to oxygen to excite it to singlet oxygen. Then you have a light source. The light source is absorbed by the photosensitizer, which then allows the photosensitizer to transfer its energy. And then there's the tissue oxygen, which gets excited to singlet oxygen. Now, in case that's not completely clear, I have a nice little diagram. You have in the cell, you have a photosensitizer, and then you have oxygen that's already hanging out. You hit the photosensitizer with light, for example, from a laser. The photosensitizer becomes excited, and then it's able to transfer its energy to the oxygen already in the cell. And then the singlet oxygen, at that point it's excited, goes and destroys DNA, causing cell damage, causing the cells to die. Unfortunately, current photodynamic cancer therapy agents could be better. So the first generation is photoprin. It's a mixture of a bunch of different porphyrins. It's currently in use. But unfortunately, since it's a mixture of a lot of different porphyrins, we don't really know which ones are actually like photosensitizing and if there's any that are just kind of along for the ride, not pulling their weight. Also, the photoprin has a really high absorption energy, which means it has a low wavelength, light being a low wavelength, which can't penetrate as deep into the skin as we would like, which means you can only target tumors very close to the surface of the skin or in your mouth or in your throat or something like that. Second generation is a very specific porphyrin, so that's good. We know what is actually doing the job that we want it to do, but it still has that problem of high absorption energy. So really, we would want to basically have a different absorption energy for a better photodynamic cancer therapy agent. So how can we achieve that goal? So porphyrins, I've already mentioned, are a really good photosensitizer. They're used in a lot of PDT. But subphthalocyanide, which I also mentioned earlier, can also sensitize singlet oxygen. Now porphyrins do sensitize singlet oxygen really, really well, but again, they have that high absorption energy. Sub-PC, on the other hand, doesn't sensitize singlet oxygen as well, but it has an absorption energy that is really attractive. It's a lower absorption energy, which means a longer wavelength, which means that it can penetrate deeper into the skin. Also, because it can absorb at 1020 nanometers, which is within the range of an NdI laser, which is around 1060 nanometers. NdI lasers are really common, and they're really easy for hospitals or clinics to get a hold of, so that would just make photodynamic therapy much more accessible if we could use ND-GAGs to use in PDT instead of different lasers. So we would really love to be able to combine those good qualities while getting rid of the bad qualities to make a better PDT agent. So there's a thing called excitation energy transfer, and I have another diagram. So you have the same photosensitizer, and you will notice I've added acceptor and oxygen, but then you can also have another photosensitizer, which is a donor. Now, in this process, the photosensitizer donor absorbs a different wavelength of light than the acceptor can absorb, but then it will emit basically the energy that is required to excite the acceptor, and then the process is the same, excites things with oxygen, and causes cell damage. So you'll notice that now we're using a different wavelength of light initially, but we're getting the same result. So my research question was, can we combine sub-PC and porphyrin in an adduct, that just means chemically bonding them, to combine those desirable qualities while getting rid of the qualities that we don't want? All right, now just a really brief note on synthesis. First I had to synthesize the porphyrin, then I had to synthesize the sub-PC, and then I put them together to make an adduct. So this is an overview of that reaction. You'll have porphyrin, sub-PC. This is one possible adduct, and yes, you have to cook it for 1 to 2 weeks, which is lovely. To simplify this picture a little bit, you can think of it like this. Now, I would like to point something out. So this is the porphyrin that I was using, and you'll see there's 4 OHs, and those OHs are where the sub-PC is going to attach. So you have a lot of possible adducts that you could make. First one is just a single sub-PC. Second one, you have 2 sub-PCs. Now, you might be looking at this and wondering, couldn't you also have 2 sub-PCs attached like that? Yes, you can. So that's a third possibility. Fourth possibility, you can have 3 like this, and fifth possibility is you can just have 4. So back to my research question. Not only do I want to see if an adduct will make a better PDT agent, but I'm also really curious about which adduct is going to be the best. So that was sort of a sub-question that came up over the course of my research. All right, so I've just given you all the introduction. Take a breather really quickly before I get into the data. So throughout all of my research, I was really looking at this process. I was looking at different parts that I will be pointing out as I get into the data. So first off, I just wanted to look at my product and really see, did I make an adduct? Do I have sub-PC and do I have porphyrin? So the way that I do that is by using UV-Vis. UV visible spectroscopy is when you have a solution and you shoot light of different wavelengths at it, and then you see which wavelengths are absorbed. You can sort of think of this as being able to tell the color of the solution. It's not exactly correct, but on the x-axis here, you have wavelength in nanometers of light, and then on the y-axis you have absorption. And then you see this purple spectra here is for the porphyrin, just porphyrin, and the pink line is just sub-PC. So if I have an adduct, I would expect to see both porphyrin and sub-PC, both of those peaks. And I do, when I did this on the adduct, I did see both peaks. Now this tells me that there is both sub-PC and porphyrin in the solution, but it doesn't tell me whether or not they're connected to each other. So that's really key. However, UV-Vis is useful for another thing. So you can use it to tell how much sub-PC there is to each porphyrin in solution. And how you do that is you compare the height of the porphyrin peak to the height of the sub-PC peak. And a 1-to-1, if you have like one peak here and the other one here, that doesn't necessarily mean that there's a 1-to-1 ratio of porphyrin to sub-PC, so you have to do a little extra calculation. But I have 3 different fractions here that I took, and you can see this light blue one has a really large porphyrin peak and a really itty-bitty sub-PC peak. So when I calculated that out, it came out to be about 0.8 sub-PCs to 1 porphyrin. So this could mean that there is some free porphyrin just hanging out in solution, not attached to the sub-PC. 0.8, however, is also within error, so this might be a 1-to-1 adduct, or a 1-to-1 solution. Then we have this dark blue spectra, and you see you have a very small porphyrin peak and a really large sub-PC peak. So when I calculated that, it came out to about 15-to-1 sub-PCs to porphyrin. Now, you might remember there's only 4 spots on the porphyrin for the sub-PC to attach. So there's a lot of extra porphyrin. That fraction needs to be purified a lot more. Yes. But this white one that we had initially, this nice porphyrin peak and a reasonable sub-PC peak, comes out to about 3 to 1. So that tells me that if that is an adduct, it's most likely the 3 to 1 adduct. So that's an important bit of information. All right, so we just talked about, yes, we have sub-PC and porphyrin, but now I really want to focus in on this energy transfer between the sub-PC and the porphyrin, because that's really what I was doing my research on. So the way that I'm going to do that is I'm going to look at fluorescence spectra. So that is when you shoot light at your sample in solution, and then you record at what wavelengths they emit light. And so for the porphyrin, you have this emission at about 650 nanometers. So you have wavelength in nanometers, and then you have intensity on the y-axis. And then for sub-PC, when excited at 510 nanometers, emits at around 560 nanometers. So what we would really like to see in the adduct is we would want to excite it at the sub-PC wavelength, and then we would want to see the porphyrin emission. And the reason that is because we're shooting this essentially yellow light at the sub-PC, so we will see some of this sub-PC emission, this orange arrow, but then we would really also want to see this red arrow coming out of the porphyrin. That's going to tell us that the orange energy transfer arrow is working. So we want to see both peaks in the adduct. And indeed, we do see both peaks in the adduct, so that's very good, which tells us that the energy transfer is working. Now, there is one more important bit of information, and that's we need to know if the adduct, that is the porphyrin and the sub-PC, being physically connected, is that really important, or is it possible to get this energy transfer if you just have porphyrin and sub-PC together in solution? So then I needed to do a control with a physical mixture where I just put 3 sub-PCs to 1 porphyrin in solution where I knew that they were not connected. And this is the spectrum that I got, and you'll see that there isn't this porphyrin peak. So what that tells me is that unless the 2 are actually connected, you aren't going to see the porphyrin emission. So it is really important that you actually make an adduct and you don't just have both in solution. Okay, fluorescent spectra can also be used for another thing, which I found when I was doing them on a bunch of different fractions. So here, just the same fluorescent spectra of a bunch of different adducts. This is the sub-PC peak, and then this is the porphyrin peak. Now you'll notice that there is a lot of difference in height in the porphyrin peak, and that's actually really interesting. We really want to see that porphyrin emission. Like I said, that was that red arrow that's going from the porphyrin to the singlet oxygen, or to the oxygen to excite it. So if we see more porphyrin emission, that's probably going to translate into more singlet oxygen, which will then cause more damage to the cell. So that's a more efficient energy transfer. It's just working really well. So we would really love to see something like that. And when I went back to my UV-Vis data and I compared the sub-PC to porphyrin ratio, this is what I found. So this top peak had a 3.9 sub-PC to porphyrin ratio, which probably means there's a lot of 4 substituted adduct with the 4 sub-PCs, but then there's a little bit of 3 substituted adduct perhaps. And then as you go down, 3.8, 3.6, 3.3, and 3.5 don't exactly follow the trend. But then we get all the way down here to 3.1, and that's this very small porphyrin peak. And that probably means that it's mainly 3 substituted adduct with a little bit of 4 substituted adduct. So from these data, I was able to tentatively say that it looks like the 4 substituted adduct is going to be the best PDT agent. Okay, so we were just looking at the sub-PC and the porphyrin, and we looked at the energy transfer between the sub-PC and the porphyrin. But, so yes, that is happening. Oh, sorry. But then we can do one more thing to really look at this, and that is going to be lifetime, looking at the lifetime. So that is examining the excited state of the sub-PC specifically. So when you excite sub-PC, it'll kind of hang out, the excited state of sub-PC will hang around for a little while until it eventually falls back down to the ground state. And there you can measure that in time, and that's called the lifetime. But if this energy transfer is happening, we would expect that the sub-PC lifetime is shorter because because of this energy transfer. The excited state is transferring its energy away and then falling back down to the ground state faster than it would if it was just on its own. So this is a lifetime spectrum. You have time in nanoseconds, that's after the species was excited, and then you have emission on the y-axis. So the pink spectra is sub-PC by itself, and then the blue spectra is the adduct. And just qualitatively, you can look at those and you can see that the shapes are very different, and that the blue one seems a lot shorter, it goes down a lot faster. So that seems, again, qualitatively, like the lifetime is shorter. And then you are able to actually calculate the lifetime from this. And what I found was that the sub-PC lifetime was about 3 nanoseconds, give or take 0.7 nanoseconds, and the adduct was 1-ish, give or take 0.7 nanoseconds. So that is significant within 1 sigma, but it's, yeah, it is. So that again is just confirming that energy transfer. Okay, so back to this. We have now looked at the sub-PC and the porphyrin. We have looked at this energy transfer, but now we really want to look at the transfer to the singlet oxygen. But in order to do that, instead of looking at cell damage, we ordered a chemical called sensor green that fluoresces in the presence of singlet oxygen. So, so then we can detect the fluorescence of the sensor green, which would tell us that there is singlet oxygen around in solution. And the reason we do that is so that we can just put the porphyrin and the sub-PC in solution. We can excite at this wavelength, and then this energy transfer should happen, and then we can see whether or not the whole process works and we're getting singlet oxygen. So this is a fluorescent spectra, so wavelength in nanometers on the bottom and counts per second, so emission on the y-axis. And this is ideally what a spectrum would look like. So this is measuring the fluorescence of the sensor green. You have before irradiation, so I had a sample that I took the spectrum, and then I irradiated it with that yellow lightning bolt light, and took another spectra afterwards. So there is a big jump, but this was only one trial, and we had some challenges with reproducibility. So what we ended up doing was using the plate reader, so we could take a lot of different samples and average them all. And we just read at 1 wavelength, so around 530-ish. And we took the initial and then the final. So we were just looking at just right there. And then the initial readings would change a lot depending on the day, even though I tried really, really hard to keep all the conditions the same. So instead of just looking at the change, the delta emission, what I ended up doing was taking the final, the ratio of the final over the initial emission, because the initial would go up and down, and then the final would go up and down proportionally, so it made sense to take a ratio. So when I did that, I found that the adduct and sub-PC on its own both had fluorescence ratios of about 1.2. So that means the final was 1.2 times the height of the initial. And then the control had about 0.8. Yeah. So basically, the adduct and the sub-PC were higher than the control. And this is not really a quantitative method. It's more qualitative. That's a limitation of the sensor green. But this, what we use this for is to say that yes, we do have singlet oxygen in solution. My adduct is sensitizing singlet oxygen. So that has been confirmed. Okay. So going back to my research questions. Will a subthalocyanine porphyrin adduct combine the desirable qualities to make a better PBT agent? Yes. If you remember back to that diagram, we confirmed that the energy transfer is happening, and we've confirmed that the adduct, the fact that it's an adduct, is important. And then I also confirmed that it was sensitizing singlet oxygen. So yes, we are able to get the porphyrin sensitizing singlet oxygen using the sub-PC wavelength. And then, which adduct is best? Tentatively, I would say the 4-substituted adduct, because that was the fluorescence looked the best for that one. It's a little bit complicated, however, because the 4-substituted is going to be the least soluble in water, and we are made up of water, so not always the best for a drug. But, yeah. So, future works, increasing yields of the reactions. increasing solubility of the compounds. In vitro and in vivo testing, really looking at whether or not you're getting cell damage. That was the only part that I haven't really tested yet. And also trying different adducts. And there are students right now working in Professor Stork's lab that are looking at porphyrins that have metals at the centers, looking at attaching the sub-PC in slightly different places. And again, just looking at even those 5 different adducts that I synthesized to see really which one is best. So just to kind of zoom back out to the big picture, PDT is a growing area of research because it's such a good alternative treatment for cancer. So what I've done is really just a small part of that, but I think it's still important because this is really how science is done. You have a bunch of different people, different labs all over the place, each giving a small bit of information, so eventually we'll have all sorts of information about lots of PDT agents, and we'll be able to design the best treatment plans for patients. So I would really quickly just like to acknowledge all of you guys for coming and listening to me, Professor Stork, for being my advisor and for guiding me through this research, all my lab mates who hung out with me, made me laugh, Professor Brandenberger in the physics department for helping me use lasers, the chemistry department, and you can read the rest. And then references. Yes. All right. Questions?
So I don't know a lot about PDT, but I do know that at least in the past, when they first invented it, there were problems with people receiving the treatment and then being really, really sensitive to sunlight when they went outside. Is that still a problem with your form of PDT?
Yeah, so what Rachel's talking about is just the light is really important to, you eventually desensitize to the function of light. Sunlight is light, so if you have PDT agents in your system, if you go out in the sunlight, you might start damaging your tissues. Yes, that is still a problem, and it's kind of complicated because it is, the light. So I don't know that this would really solve that problem. Definitely something we need to look into.
Yes. Are there any other health complications that you know about for sub-PC or porphyrin or the adduct?
I know, I guess you do have to be careful when handling them in the lab. You're supposed to wear gloves and things like that. So yes, they can be, there probably are some health concerns that you just have to very carefully control. But a lot of cancer drugs, are essentially damaging your own tissues. So they all have risks.
Perhaps a trivial question, but by what mechanism does the photosensitizer give the energy to the oxygen?
To the oxygen?
Yeah.
Well, it emits energy. It doesn't exactly emit light, but it emits energy, and it's the right amount of energy to sense. I never did this, so you're just.
They're talking to each other.
Yeah.
How targeted an intervention could this be? If there was a tumor, in the intestine, could you get this adduct to the intestine and move?
Yeah.
There's other complications.
That's an excellent point. It is very targeted. You do have to be able to get a light source wherever you're going, but yeah, because you can target where you actually put the adduct. So you can inject it exactly in the area that you want it, and then you also target where the light is, where you're shining the light. And that's actually really important. The light in the absence of the photosensitizer and the photosensitizer in the absence of light should not be damaging. So you can really target this to a very, I guess as small as your laser beam is.
Another, just with the wavelength of laser that you were looking at using, or were using, how deep can you get into somewhere?
I don't actually know centimeters or millimeters. but it is deeper than current treatments allow.
Current treatments use 700 something nanometer light. It's in the very near IR that we use, and this is more far near IR. It's still technically near IR, but it's lower enough energy that goes deeper. So it's some reasons.
Thank you very much for an excellent talk.